All right, here's the start of the third video. I'm looking at number 8. For each problem, find the volume of the solid that results when the region enclosed by the curves is revolved about the y-axis. So at this time, I need to set this up like the integral from c to d of f of y squared minus g of y squared dy, and I'm going to multiply that by pi. In this case, I got two functions. Because it's f of y, these should look like x equals. So it's like x equals y squared plus 3, x equals 1. They're giving us two y values. These are going to be the c and the d. If you tried to see where these two values intersect, like y squared plus 3 equals 1, you subtract 3, get y squared equals negative 2. If we took the square root, we would get get like a complex number. And what this looks like graphically, x equals y squared. So y squared is rotated 90 degrees clockwise. Just like x squared, it's got that quadratic shape. If you had x squared and I added 3, this would shift the function up 3. When I'm looking at y squared plus 3, it shifts this 3 to the right. So there's the function x equals y squared plus 3, and the other function here is x equals 1. Now they also told us that we were going to revolve this about the y-axis at y equals negative 1 and y equals 1. So I'm going to zoom in on this part here, take a screenshot. This is the area that I'm highlighting in yellow that we are trying to revolve around the y-axis. So we're looking at dy. This function here in red is my f of y. The function in blue, even though it's a straight line, is my g of y. And these two values here, this one at 1, negative 1, and at 1, 1, this value and this value are my bounds. So if I go, I'm going to hit done, save the photos. If I go back here, I'm going to set this up like the integral from negative 1 to 1 of y squared plus 3 squared minus 1 squared dy times pi. Because we're revolving this around, we're integrating the area and we're looking at areas of circles. Please, 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 when we're looking at squaring something, don't tell me it's just y to the 4th plus 9. There's those terms in between. This looks like y to the 4th plus 6y squared plus 9. Remember, the cheat of a plus b squared is a squared plus 2ab plus b squared. So it's like 3 times y squared times 2. And we're still subtracting 1 dy. Still multiplying by the constant of pi and evaluating this from negative 1 to 1. So this becomes y to the 5th over 5 plus, this is going to be 6y cubed over 3. I'd probably write it like it's 2y cubed. And then the plus 9 minus 1 is 8, so this is plus 8y. Still multiplying by pi. I'm evaluating this from negative 1 to 1. I'm going to do 2 different colors at 1. Because the constant pi is here, I'm going to put a bracket and we'll multiply by that at the end. Here is like the antiderivative at 1. So it's 1 to the 5th divided by 5 plus 2 times 1 cubed plus 8 times 1. And the reason why I'm trying to do different colors is I'm going to be subtracting negative 1 to the 5th over 5 plus 2 times negative 1 to the 3rd plus 8 times negative 1. So it's like pi times 1/5 plus 2 plus 8, and then minus, this is going to be a negative 1/5 minus 2 minus 8. Or pi times 1/5 plus 10 minus a negative 1/5 minus 10. Because I'm subtracting, it's going to change these signs. So this would really read like 1/5. Taking away a negative 1/5 is 2/5 plus 20. All of this times pi. If I'm trying to write 20 as something over 5, I would need to multiply by 5 and say this is 100/5. So I could think of 100/5 as the 20. 2/5 plus 100/5 is 102/5 pi. And just, we generally speaking kind of treat pi like we would a variable, and you write the number first and then that number pi. Okay, for number 9 and 10, when it's asking us to find relative max and min, this is like saying that the local max and min, where there's possible high points and low points. At all of these points, we're looking for critical numbers where the slope is going to be equal to 0. There's 2 ways to go about these. You can do the first derivative test or a second derivative test. I'm going to start by looking at number 9 and taking the derivative here. This is negative x to the 4th, so it's negative 4x cubed plus 2x squared. The derivative will be 4x. And the derivative of x is derivative of negative 2 or subtracting 2 is going to be 0. I'm taking my derivative and I'm setting it equal to 0. Sorry, I think I'm going to zoom in more. The pencil did. So this is going to be equal to 0. If I'm setting these equal to 0, I really think the best bet for these is going to be factoring. I really also believe that you guys have an easier time seeing when the larger degree for x is positive. So I would try to factor out a negative 4. They both share a 4. I could factor out a negative 4. They both have an x. So we'll do negative 4x times. This becomes x squared. And if it was negative 4x here, positive 4x, and I'm factoring out the negative 4, this becomes minus 1 equals 0. You could have written this like negative x squared plus 1 and still done the same thing. So I'm trying to figure out when this will be equal to 0. Again, just for what we're going to be using the derivative for, I think it's easier to see it like it's negative 4x times x minus 1 times x plus 1, and I'm setting this equal to 0. So I need to figure out when each of these factors are going to be equal to 0. So when negative 4x is equal to 0 is x equals 0. When x minus 1 equals 0, that's x equals 1. Sorry about the barking. And x plus 1 equals 0. I subtract 1 on both sides to get x equals negative 1. So now I'm going to make my table here at the 3 values. Negative 1, 0, positive 1. Actually, let me lower this a little bit. We're going to test out what happens at each of these values for our derivative. Again, this is, I didn't label it, but our f prime of x, the derivative, or you could call it y prime, is the negative 4x cubed plus 4x. I'm going to be evaluating it here. And I think it's easier to see what the sign's going to be when all of the factors are there. So if I were to choose a value that was to the left or less than -1, let's say x equals -2, it would look like -4 times -2, -2 minus 1, -2 plus 1. Negative times a negative, this is going to be a positive. -2 minus 1, I don't care, that's -3 so much that it's negative. And then -2 plus 1 is going to be a negative. So here, before 1 is going to be positive. In between -1 and 0, let's use x equals -0.5. -4 times -0.5 times -0.5 minus 1 and -0.5 plus 1. These two are going to be a positive. This is going to be a negative times a positive. So the in between here is going to be negative. Some value between 0 and 1. I'll choose 0.5 again. So it's -4 times 0.5. 0.5 minus 1 and 0.5 plus 1. These two are a negative times another negative times a positive. So this is going to be positive here. And for the last one, I'll use x equals 2. -4 times 2, 2 minus 1, and 2 plus 1. These two are negative. This is a positive and a positive. So here it's a negative. All right, so I didn't give myself a ton of room, but we have a couple changes. Remember, this table, what I'm trying to show here is where the first derivative is positive and negative. So I could look where this is going to be increasing and decreasing. So if my function is increasing and then changes to decreasing, this is going to be a potential max. If I go from decreasing to increasing, over here is going to be a potential min at 0. And if I'm going from increasing to decreasing again, this could also be a potential max. I'm showing all of this with the first derivative. I'm going to try to copy all this and see if I can show you guys the second derivative. Copy. So if you didn't want to go through and test out the values, you could take the second derivative and look at the concavity. Just quickly before we go more into this, if something is concave up, that means the second derivative is greater than 0, positive. If it's concave down, that means the second derivative is less than 0, negative. If you know something is concave up like a cup, and you know that the first derivative, the slope is 0, then we know that this is going to be a potential min. If you know this function is concave down on some interval, and you know the first derivative is equal to 0, this is going to be a potential max. So my first derivative was -4. So like f prime of x was -4x cubed plus 4x. If I take the derivative again for that second derivative, I get -12x squared plus 4. All right, again, I'm going to factor out a -4 here. So I get x squared minus 3. And when I set this equal to 0, I'm going to get x equals plus or minus the square root of 3. I could add 3 and then take the square root. So I want to overlap. Let me see if I've got enough room to paste. So knowing that I had for the first derivative, I'll do it actually in red. For the first derivative, those critical values were at -1, 0, 1. I now have my inflection points. Well, I now have my, spots where the second derivative is going to be 0 between negative square root of 3 and the positive square root of 3. The square root of 3 is going to be larger than 1. And we got the negative square root of 3. It's going to be to the right of -1. This doesn't have to be super precise, but you can think about the values in between. So if I'm trying to figure out some value between negative and positive square root of 3, I might pick x equals 0. If I substitute in 0 into this function, I'm going to get -12 times 0 squared plus 4. This is going to be a positive. If I substitute a value that's larger than the square root of 3, let's do like x equals 10. This would be like -12 times 10 squared plus 4. This is going to be -12 times 100. This is going to be negative. And a value that's going to be less than negative square root of 3. We could do another extreme one like -10. Same idea, because it's squared. -12 times -10 squared plus 4. That's going to be -120 plus 4. That's also going to be negative. So this is telling me concave down, concave up, concave down. And you could use this to try to make a claim about whether these are going to be relative maxes or mins. All right, I need to see the next one. Sorry, I just got to go to this one here. Actually, let's see how we did for this part. Yeah, so we're talking about the max. The minimum was going to be at 0. Oh, and they were looking for the actual point. Remember, if we're looking for the actual point on here, let me go to this last one. You would need to take in these values, these x values of -1, 0, and 1, and plug them into here. All right, so let's do the same thing with number 10. This is our function. We're going to take the derivative. This would be 4x cubed minus 6x squared. I know it's written in terms of y, but we can call this the f prime of x. If I'm setting this equal to 0, I would factor out a 2. Oh, sorry, that's not squared. That is supposed to be 6x. Factor out a 2x, I'm left over with 2x squared minus 3 equals 0. This term 2x set it equal to 0 is going to get me x equals 0. If I set 2x squared minus 3 equal to 0, I'd add 3 on both sides. 2x squared equals 3. And then divide by 2 to get x equals plus or minus the square root of 3/2. Now, it's okay if you're not sure exactly what the number of 3/2 is going to be. For this case, we just need to set this up where it's going to be testing out values in between. So the negative square root of 3 over 2. Oh, let me make sure I'm writing all this inside the square root. And you could write these like it's 2 square roots. Like you could say it was negative square root of 3 divided by the square root of 2. Or you can put the whole fraction inside the radical. Okay, so if I'm trying to look at values in between, again, I'm testing out at this spot here. If I want to pick a number to the left, it doesn't have to be something that's smaller. I could do like x equals -6. If I did 2 times -6, all of that times 2 times -6 squared minus 3. This would be a negative. negative 6 squared times 2 is going to be a positive 36, then times 2 is 72, so this will be a positive. So before negative square root of 3 over 2, this is a negative. The square root of 1 is 1. The square root of 4 is 2. Because 3 divided by 2 is greater than 1 and less than 2, I could use 1 to test out in between here. If I said x equals 1, negative 1. Negative 1, and multiply that by 2, then multiply 2 times negative 1 squared minus 3. This will be a negative. Negative 1 squared is going to get me 1 times 2 is going to be positive 2, and minus 3 is another negative, so I'm positive in between here. That was at x equals negative 1. I'm going to use positive 1. 2 times 1 times 2 times 1 squared minus 3. This right here is a positive. This is going to be a negative, like 2 times 1 squared is 1, times 2 is 2, and then minus 3 is going to be a negative 1. So that's negative. And again, you can just choose numbers that are larger. It doesn't have to be close if we're just trying to see for after the square root of 3 over 2. I could do like x equals 4. 2 times 4 times 2 times 4 squared minus 3. Sorry, that's squared. This will be a positive, and this will be a positive. So again, at this point, we could use that this is going to be decreasing, increasing, decreasing, and increasing again to make the claim about what this is going to be. Or we could go like the last one, where if we know that these are going to be, concave up, concave down, they can tell you about if it's going to be a min or a max. And if you check on here for the answer key, let me jump to that page. For number, where was it? Oh yeah, for number 10, people were getting a little bit thrown off about the negative square root of 6 over 2. If we have the square root of 3 over 2 as an answer, I can write this like the square root of 3 over the square root of 2. We don't want to have the radical in the denominator, so I can multiply the square root of 3 over the square root of 2 times the square root of 2 over the square root of 2. When we multiply, we can write this like it's the square root of 6 over the square root of 4, or the square root of 6 over 2. So we're talking about the same number, we're just representing it in a different way, and then they get this value by inputting it into the function. All right, for numbers 11 through 13, they're trying to ask us to find the absolute maximum on the given interval. The first two have negative infinity to infinity as an interval, and then the last one has a closed interval. We're still going to do the same thing. We're going to take the derivative like we did before. In fact, this one's really similar to the last one. I get 4x cubed minus 4x. If this is my derivative, I set this equal to 0. Again, I can factor out the 4x. I get x squared minus 1 equals 0. This is going to look like 4x times x minus 1 times x minus 2. Oh, sorry, not minus 2. Plus 1. So I'll get x equals 0, x equals positive 1, x equals negative 1. So before this, again, I can use my factored form of the derivative to help me figure out what the sign of this is going to be. Let's say x equals negative 2. 4 times negative 2 times negative 2 minus 1 times negative 2 plus 1. This is a negative, and another negative, and a negative. So 3 negatives here make this negative. At some value between negative 1 and 0, we'll choose x equals negative 0.5. 4 times negative 0.5 times negative 0.5 minus 1 times negative 0.5 plus 1. These two will be a negative, this will be a negative, the last one will be a positive, so this is a positive. between 0 and 1, I'll choose x equals positive 0.5. 4 times 0.5, 0.5 minus 1, and 0.5 plus 1. So this is a positive, a negative, and a positive. It's negative. And then the last one here, I'll just choose x equals 2. 4 times 2, 2 minus 1 times 2 plus 1. All these are going to be positive. So, when we're looking here, if we're looking for an absolute min or an absolute max, we're looking at the change. This is going to be decreasing, increasing, decreasing, and then increasing again. Now, if we're talking about everywhere, and we know our function is a positive, even function, whether it was x to the 4th, whether we're talking about x squared, x to the 4th, x to the 6th, x to the 8th, any even exponent here for the degree, for the largest exponent, we're not going to be able to say that there's some actual max because we could keep on zooming out and it keeps on increasing in both directions. So, if I go from decreasing to increasing, at -1, this would be a possible min. If I go from increasing to decreasing, this could be a max. And then if I go from decreasing to increasing again, this could be a possible min. Without the graph, like you wouldn't be able to just open up Desmos, we would input these values. So it's -1 to the 4th minus 2 times -1 squared minus 4. If I called this f of x, this is like f of -1. 1, -1 squared is 1 minus 2 minus 4. This is going to be -1 minus 4. We get -5. And then at +1, 1 to the 4th minus 2 times 1 squared minus 4. Same thing, 1 minus 2 minus 4. I get -5 again. At 0, f of 0 looks like 0 to the 4th minus 2 times 0 squared minus 4. So this is just going to be -4. But knowing that this is going to be a even function, I can show x to the 4th minus, x to the 4th minus 2x. So these are the points that we're talking about. I've got 2 possible mins, but if I don't have a closed interval, right, like I'm not stopping this. Let me see if I could bring this up. If I were to suddenly give this some bounds and say this went from like -3 to, I'll use negative. If I suddenly put bounds in this, I would have to find the points where the slope is equal to 0 and test out the endpoints to be able to say if there's going to be a max or min. All right, I'm going to stop this video here and then continue to make more. If you have any questions, please feel free to reach out.